Hi, in this lecture I'm going to talk about why it is that having a linear restoring force, like a mass attached to the end of a spring, why that leads to simple harmonic motion, those sinusoidal oscillations. And we're going to do that by talking about a concept that really is a different way of doing physics compared to what you've been doing so far. And this concept is called an equation of motion. Let me sort of summarize what the thinking is, so the shift in our thinking that we're going to meet for the first time here, but we might again, or we will definitely meet again later in the course. So here's how you've been doing physics. You ask what's the current situation and what happens next. So for example, let's go back to your mechanics courses, maybe you've got a projectile motion problem, and you ask where is the thing starting, how fast is it going, where is it going to end up, how high is it going to fly, how long is it going to take, and so on. Right? But you start some sort of initial situation, and then you calculate how that situation changes. And that's okay. So now here is a new way of doing physics. That is essentially what equations of motion are about. And we'll see that in practice in a very simple example here in simple harmonic motion. And we'll meet it again later in different situations. So here's how we're going to do physics now. Instead of starting with a specific situation, we're going to start just with the laws of physics. We're asking what sorts of motion do the laws of physics allow for? What's allowed to happen according to how physics works, how nature works. So that'll give us a lot of different possibilities. Right? We put our laws of physics, and it won't say only one specific thing is allowed to happen, but a whole range of possibilities. In the case of simple harmonic motion, we'll see it allows for oscillations of all sorts of amplitudes, maybe all sorts of angular frequencies. And then you might have a specific situation, and we can pick out of all those possibilities that the laws of physics allow for, what's the one that that's actually occurring, right? So applied to the situation of projectile motion, instead of saying here's where we start and how fast we're going, where is the thing going to fly next, we're saying if something accelerates just under gravity, what sorts of motion is allowed to happen? Oh, okay, essentially parabolic motion is the upshot. And then we can find, for a particular situation, a particular ball being thrown, a particular arrow being shot, whatever it is, we can find the particular trajectory out of all those infinite number of possible parabolas that are allowed by the laws of physics, essentially Newton's second law, with the force just being weight. Out of all of those, we pick the one that applies to the specific situation we're looking at. And the advantage of doing that, or one of the advantages of doing it, is that the focus is on trying to understand the underlying physics more so than the specific situation. For example, more often than not, as physicists or as scientists more generally, we're interested in how does nature work? Right? What are the underlying principles? What are the rules? And to explore that, we don't ask about a single specific situation, what happens next. We wouldn't really know where to start. We look at a proposed law of physics, we ask what are the consequences, what sort of things does it allow to happen? And then we can check individual situations to see if they match what those laws predict. It's a fairly subtle change, but it's really a most advanced way of doing physics. So let's apply this way of thinking to the system we've been studying recently, a mass on a spring. So what's the relevant law of physics here? Well, it's a theory of mechanics. It involves forces, so Newton's second law is going to be key. Yes, also the other Newton's laws, but to figure out what possible motion is allowed, we'll definitely need to understand acceleration, mass, and so on. The relevant law is Newton's second law. Now, of course, Newton's second law is really kind of a placeholder for lots of different laws, depending on the type of interaction that is relevant to the type of system we're studying. In our case, the force is a spring force, so Newton's second law says ma, right, is the force, which in our case is minus kx. I'm not making any specific assumption about where the spring starts, how far it is squished, stretched, where the mass is. I'm just writing down the law of physics that has to hold for the system. Right? That has to be true no matter what. Now, I'm going to show how this leads to simple harmonic motion, to the sinusoidal position versus time graph, and velocity versus time graph, acceleration versus time graph. Right? It's sine curves, sine, cosine, and so on. Why is it? Yes, we observed it experimentally. It seems to be true. The math works out, but can we prove it? That is what has to happen in this kind of situation. So this is our starting point, and now I'm just going to work with this to figure out what does it allow. Now, what's crucial to understand here, of course, is that this applies at all times, and both a and x are changing with time, so they're functions of time. Now, a and x, they're related. Right? A is the time derivative of the velocity, which in turn is again is the time derivative of the position. Excuse me. All right, let's write this down. Change my color because this was kind of the key starting point. So, but now I'm going to use that a is, let's write out in full, it's dv dt, because v being a function of time, therefore is the second time derivative of the position. This is a function of time. So I can rewrite Newton's second law. I'm going to get that m d2x dt squared is equal to minus kx. So this is really just Newton's second law, but rewritten in a way where I plug in for the acceleration, what the acceleration literally is in terms of the position. This is the thing I'm going to call the equation of motion. Right? It is Newton's second law, but with the relationship between a and x made explicit. So it is an equation that relates the second derivative of a variable, namely x, second time derivative of x, to x itself. Now, in a different system with different forces, it would look different. I'd get a different equation of motion. And in fact, systems that are not directly about forces can also have equations of motion, but that is maybe the subject of a more advanced course, mathematical or physics. We're going to deal with this equation of motion. So what is this telling us? What is this telling us? Let's write it out in words. It is saying the laws of physics are such that the second time derivative of the position of a mass on a spring, that second time derivative is proportional, let me write it, is just equal, proportional with a certain constant we know, is equal to minus k over m times the position. I'm just putting the equation in words right now. So now we ask, well, what function of position, what position as a function of time makes that true? What functions x of t make this true at all times? Because Newton's second law holds at all times, doesn't hold just now. It always has to be true. I want to find some function such that its second time derivative is equal to the function itself up to a minus sign and some constants. That is our goal. The equation of motion is a differential equation, right? It means it's an equation that relates a variable to its own derivative. In this case, it's a second order differential equation because it relates to the second derivative. And of course, I forgot to put the 2 right here. Now, you may have taken a course on differential equations before, in which case you should have no trouble solving that. You can probably anticipate the rest of this lecture. If you haven't, don't worry. In this course, we're not going to demand that you're able to solve any equation, any differential equation that you might come across. But what you'll be able to do, what you should be able to do, is to understand essentially where they come from, in the case of equations of motion, what they mean, how to interpret them, and what we're trying to look for. Right? We're looking for not a number x, not a value of position, but a function that tells me for all times where the object would be. So we're looking for a function. What is this function? And the way we're going to do it is solving it, not knowing where to start. That can be difficult. That's what a differential equations course is for. And if you haven't taken it, I recommend that at some point or another you do take it. Because you're not going to be able to get away from differential equations if you're trying to do physics. But what we're going to do instead is we're going to try functions, and then we're going to check whether they satisfy this equation. Let's write this down. So what's our strategy? Try, let's call them informed guesses of what x of t might be. And by try I mean we're going to check whether it makes the equation of motion true, whether it satisfies it. It's a term we use in mathematics. Whether the proposed function x of t actually makes the equation of motion true at all times. Right, so that is our strategy here. Okay, so let's just to illustrate the point, I'm going to make a bad guess first. So guess 1. Let's say I look at the system on the spring, and I see the equation of motion here, and I say, well, maybe it'll be true if x of t is given by some constant times t squared. That's my proposed function. So how about x of t, this could be x, our first trial of t, right, is equal to, let's give it some constant, maybe call the constant c, t squared, for some yet undetermined value of c. So I'm not fixing the function completely, I'm just saying maybe it's a quadratic. With some c, maybe I can figure out what c is. Value of c, but it's a constant. So how about this? Well, let's try it, right? Our equation of motion is this. So I'm proposing x of t is c times t squared. So that I need to find a second derivative. Right? So then I have that dx dt is going to be 2ct, right? You can easily take the derivative of this, and d2x dt squared is just 2c, right? I take the time derivative of constant times t just goes away. Let's try this now. Does this make our equation of motion true? Well, the left-hand side of the equation is m times the second derivative. So the left-hand side, LHS, left-hand side of the equation of motion, ELM, right? Left-hand side of the equation of motion. Lots of abbreviation here. What's that? It's going to be m d2x dt squared, which I figured out what d2x dt squared is, 2c. It's 2cm. 2 times c times m. Okay, it's okay. I can live with that. What about the right-hand side? Right-hand side of the equation of motion. Well, the right-hand side is supposed to be minus kx. So I know x is just, I proposed x is just ct squared. So minus kx, that is equal to minus k times c times t squared. So now the question is, are those two equal? So is it true that left-hand side equals right-hand side? Now I can, oops, what did I do? This should be, yeah, no, this is right. 2cm, i.e. is 2cm equal to minus k c t squared. Well, depends on the value of t, right? I mean, there's a c here, there's a c here. So the answer is only, that's true only if t is equal to minus 2m over k. Sorry, the square root thereof. Okay, it's really going to get us into some trouble. Right, I guess m or k, I mean, if they're both positive, you may already suspicious here, right? But even if there was a time, like even if there was no minus sign here, it's not true that the equation of motion is true at all times, right? So equation of motion not true at all times. What does that mean? If the equation of motion is not true, that means the laws of physics don't apply if that were indeed our the correct function that describes the position of the mass. But the laws of physics do apply. That's the whole point of doing physics, right? You're trying to figure out what those laws are. So that implies x of t equals ct squared is not physically possible. Right. So the logic is we propose a function, we say is the left-hand side of the equation of motion equal to right-hand side, and we check. I mean, in a sense, we could stop here, right, at this point here, because we can see right away that if I plug in different values of t, I'm going to get different values on the right-hand side. The left-hand side is always the same. they're not going to be the same for all t. Maybe I can solve for t, and this is a square root of a negative number. Okay, that also means trouble. We would make t a complex number. But even if that weren't the case, the fact that there's essentially only one or maybe two values of t that make this true means that the laws of physics are not being observed at all times, if indeed this were the function that describes the position of the mass over time. So the only conclusion is that it is not the right choice. So now let's make a better guess. That was our first guess. Now, if you have studied differential equations, right, you don't have to guess. You can look at this and you know techniques to solve this to get to the answer without wild guessing, right? And of course we can't guess all possible functions that there are. There's an infinite number of them, so how would we ever find one? Well, in our case, what we can do is we can look at what we've observed and try if that works. Guess 2. We observed x of t is equal to some constant sine omega t plus phi 0. Right? It's essentially doing experiments, we look at the graph and we find that this kind of functional expression, this function of times, the sine function, that seems to experimentally describe the right kind of motion, the kind of motion that we actually observe. So let's check this. Let's check whether this actually gives us the right answer. So again, we have x, we need the second derivative. So I'm going to find the first derivative first. First derivative is going to be a omega cosine omega t plus phi naught. Essentially, we did this before, differentiating this function. And the second derivative is d to x dt squared, which is going to be minus a omega squared, because cosine goes to minus sine, and the thing that multiplies the variable comes out. That's essentially the chain rule. Omega t plus phi naught. Right? And now we ask, well, is the left-hand side of the equation of motion equal to the right-hand side? So left-hand side of the equation of motion, what's that? It's, let's double check, what does it say? M d to x dt squared. M d to x dt squared, we write it out so we don't forget. Well, I just figured out what it is. It's minus a, I guess the m needs to be in there, omega squared sine omega t plus phi 0. What about the right-hand side? Right-hand side of the equation of motion? Well, the right-hand side is just minus kx. This is a fairly simple equation of motion. Minus kx. So x itself is this, so this is just minus k a sine omega t plus phi 0. So now we're asking, are those two the same, right? The equation of motion expresses our law of physics. It expresses Newton's second law applied to a linear restoring force. Mass on a spring, but more generally any linear restoring force. So we are asking, is it true that the left-hand side is equal to the right-hand side? It's an equation, it better be true, right? Previous example, or previous guess, it wasn't true, so it was a bad guess. But let's check this one. Left-hand side, i.e. left-hand side is this, minus a m omega squared sine omega t plus phi naught. Notice that we didn't specify what those constants are. There are 3 constants, this one, and this one. And we left them open. Right? We didn't decide that they had to take any value, didn't correspond to any specific situation. We just proposed this function that was a general sine function with an arbitrary amplitude, an arbitrary rate of oscillation, and an arbitrary shift of the phase, an arbitrary phase constant. We know, of course, what those values represent physically, but in a sense, mathematically speaking, just introduce three constants that give us this general function, a general sine function that's arbitrarily large, arbitrarily fast, arbitrarily shifted. So we are asking, is this equal to the right-hand side? Right-hand side is this, minus Ka sine omega t plus phi naught. Now this looks more promising, right? So we can cancel out. I'm asking, right, are those two sides the same? Let me put a question mark here. Now, those two sides are the same. Well, this sine function is always the same as this. Let me sort of color code this. So I identified as, okay, this thing is this thing. That's okay. They're always the same because they're literally the same function. There's minus a and there's minus a. What about the rest? Well, I left those undetermined. Right? I didn't specify what omega is, what m and k they might be given by the physical situation. But so the answer is yes, true for all times, because the time dependence essentially cancels out as I cancel out the two sine functions. Right? They're the same in both left-hand side and right-hand side. True for all times t, all values of t, provided there's a condition here, right, that those two, m omega squared, is actually equal to k. If that's not true, it'll never be true. It'll be like 5 times sine omega t plus phi naught is equal to 3 times sine omega t plus phi naught. Well, that's total nonsense. Right? It's only true if this part here is equal to this part here. Let me color code those, kind of the leftover bits. The things that don't occur on both sides, provided m omega squared is equal to k, i.e. omega is equal to the square root of k over m. So, we've shown that the equation of motion, Newton's second law applied to a linear restoring force, allows for sinusoidal motion to occur. But only if that sinusoidal motion occurs with a specific value of omega that's equal to this. It doesn't say anything about a value of phi naught that cancels out completely. It doesn't say anything about a that cancels out. Right? So, let me write this down too. But a and phi naught remain arbitrary. So we've got solutions, right? So the laws of physics say that you can have sinusoidal motion provided this is true. The laws of physics allow position versus time graphs, or essentially trajectories in space, a sine of square root of k over m t plus phi naught for any a phi naught. You get to pick those values. And physically, what does it mean? Physically, it means I get to pick the amplitude. I can just, start the spring, start the mass, pull it further back. I can start it a little bit earlier, a little bit later in time. That'll just change the phase constant, like how far left or right is the graph shifted along my time axis. Those are choices I can make. They're allowed. There's no choice I can make regarding omega, the rate of oscillation. Right? That is given by the mass and the spring. The laws of physics say you can't pick that. That is determined by those values. You get to pick those. And so if I've got a specific situation, a specific spring and a mass, okay, that fixes k and m, I can pull it down or to the right before I let go by a certain value of a, okay, I get to pick that, and that leads to allowed physics. But there's nothing I can do to change this, for example. Okay, so that is the fundamental idea of applying this equation of motion way of thinking. And we'll be doing more of it. We'll be doing more of it in the context of oscillations. And we'll be looking at some more complicated equations of motion. And we'll be doing it again when we're looking at waves, and specifically the wave equation. But right now, right, the important part is that you understand the logic of what we did. Right? The logic was, let me go back for a second. The logic was, here's a spring, that's the system we're trying to analyze. We ask, what is the physics? What are the laws of physics that apply to it? Okay, that is it. Right? This is Newton's second law. We plug in what A really is. A is not unrelated to X, right? Those two functions, they're related. One is the second derivative of the other. Okay, this is my equation of motion. This equation says only functions x of t, only trajectories of position in time are allowed that obey this equation, that make this equation true at all times. So then we use our differential equation knowledge to solve this. Now, if you haven't taken a course in it, it can be difficult. You can maybe look it up online or in a reference book on differential equations. But in our case, we sort of made an informed guess, right? So we're asking what functions of x of t make this true at all times, and we made two guesses. Where's our first guess gone? Our first guess is here. First guess was, I'm saying x of t it keeps getting bigger as time goes by, so the mass moves further and further away as time squared, right? Because this value will get bigger and bigger and bigger. We know that was going to be nonsense. But now the math says, hey, no, this just doesn't work out. Physics, you've got a mass on a spring. This motion is not allowed to occur. Our second guess was much better. Here it was informed by experimental observation. So we guessed, we checked that indeed the left-hand side of our equation is the right-hand side of our equation. But only if this connection holds, right? A can be whatever, 10. Okay, 10 here, 10 here. If this rest is true, it's true. 100 here, 100 here, doesn't matter. The value doesn't matter. The value of A does not determine whether or not this equation is true. The value of phi naught does not determine whether or not this equation is true. Right? The sign thing completely cancels out. The time dependence cancels out. That's crucial. Because if there was still t somewhere, like if there were a t here, then this would no longer be true for all times, right? The time dependence has to cancel out. And we observed, yes, it all cancels out. The only condition that remains is that this is true. Physically, this is telling us that oscillatory motion is possible, sinusoidal motion is possible, but only with a specific angular frequency. That is the logic, right? And in any specific spring I can give you where you pull it down a specific amount, well, that pulling the spring to left or right before you let go by a specific amount, that will determine A. When you let go might determine phi naught. Then you've got a specific x of t with 5 sine squared k of m plus pi over 2. Right? Sure, that's a specific example, a specific instant of this general motion. But the laws of physics allow for this for any value of A and phi naught. So think about this logic, see if it makes sense to you. Maybe when you lie in bed tonight, just think through the steps again so you can follow. So when we're going to be tackling more complicated equations of motion, where the algebra is a little bit more complicated, well, hopefully you won't get lost in the fundamental reasoning of what we're doing. But this kind of thinking is what allows us to essentially elevate the physics we're doing to a somewhat more advanced level in terms of how we look at theories, how we look at the laws of nature and specific situations to which those laws of nature apply. Let's see you in class.